All right. I tried to record this once and then I had a computer crash right at the end. So I've already written it out. I'm going to talk through it. We've talked about how to form epoxides. Now I want to talk about how you can react epoxides. Um, and to do that, I'm going to start by talking about some of the features of an epoxide that make it unique. Most ethers are pretty unreactive, they don't do much. Um, The HOMO of an ether is the lone pair on oxygen. The LUMO is the sigma star CO. So in a typical ether, sigma star CO is an okay acceptor, um, but we've seen in substitution and elimination reactions that OH minus or OR minus, those aren't good leaving groups for an SN2 or an E2 reaction. Um, so typically um, sigma CO bonds and sigma star, our sigma CO orbitals and sigma star CO orbitals don't get involved in reactions very often. Um, but in an epoxide, we have ring strain. And because the orbitals, um, the sp3 hybrid orbitals are 109 degrees apart, but our bonds are only 60 degrees apart, um, these orbitals don't overlap as well as they normally do to make a sigma bond. Therefore, if I compare a typical sigma CO and sigma star CO, because there's not as good overlap, um, there's not as much stabilization of the bonding orbital, and there's not as much destabilization of the antibonding orbital. All right. So poorer overlap means less stabilization of sigma CO, and it means less destabilization of sigma star. All right. And because of that, my sigma star CO in an epoxide is going to be lower in energy. Lower energy LUMO means better acceptor. Um, so because I have a better acceptor, that's going to make epoxides more reactive and more electrophilic than our typical ethers would be. All right. So that's the point. Um, Taking that as our starting point, what's one more thing I can do to make my epoxide into an even better electrophile? Well, I can react it under acidic conditions. And under acidic conditions, my first step is going to be to protonate my epoxide. When I protonate my epoxide, that activates it as an electrophile. Remember that positive formal charge brings the orbital energy down for all the orbitals involved uh, with this oxygen atom. So now my sigma star CO is even lower energy. So I have a great electrophile and I have a so-so nucleophile. In this case, I'm using methanol. You could use water or any alcohol as the nucleophile. Um, Notice that my protonated epoxide looks a lot like a bromonium ion, which we've seen before, and we're familiar with how the bromonium ion reacts. Um, so, because of that similarity, we're going to expect similar reactivity. Okay. When we've attacked a bromonium ion before, we've said, well, if it has a more substituted side and a less substituted side, the more substituted side is going to be more carbocation like. There's going to be more positive charge around that carbon than around the other one. Um, Same is going to be true for a protonated epoxide. When we attack it, we're going to attack the most substituted carbon, open it up. What happens there is an inversion of stereochemistry at that carbon, whereas the other carbon, no reaction is happening over here. So my stereochemistry there stays the same. So I protonate, I attack with my nucleophile, and then my last step is going to be call sol, deprotonate, get to a neutral product. Okay. Um, I want to point out this reaction sequence is very similar to the reaction where we added Br2 and an alcohol directly to an alkene. For funsies, you should go back and review that mechanism, try and draw yourself a mechanism for this reaction. But notice it gives us a very similar outcome, just with bromine in the place of my OH group. All right, so we can open epoxides under acidic conditions. Next, we'll talk about how it's different if you do this under basic conditions. All right, let's move on and talk about what happens under basic conditions. So here I'm going to react with the same nucleophile essentially with methanol, but in this case I have sodium methoxide. First thing I'm going to do is eliminate that spectator ion, the sodium plus ion, turn this into an anion methoxide, and I'm going to use that as a nucleophile. Now notice the difference. In the first case I had a great electrophile and a so-so nucleophile. And in that case, the electrophile is in charge. So the electrophile decides, okay, where do I want to get attacked? And it wants to get attacked at the more substituted carbon. Under basic conditions now, roles are reversed because now my nucleophile is the thing that has the charge. So I have a great nucleophile. My epoxide is just an okay electrophile. And therefore, the nucleophile is in charge, and it's going to say, okay, just like in an SN2 reaction, I'd rather attack the more accessible acceptor orbital. So I have two options, two sigma star CO orbitals. I'm going to attack the less substituted one. Notice when we do that, it's going to invert the stereochemistry at that carbon, but it's not going to change the stereochemistry at the other carbon. In this case, my last step is going to be to reprotonate, because when I open the epoxide, now I have a negative oxygen. I'm going to reprotonate that from the solvent to get my product. So similar reactions, just slightly different conditions, and we get a different result. So epoxides are kind of fun in that they give us this control using acidic versus basic conditions. They give us control over the outcome. Next, I'm going to show you a specific kind of product that we can make synthetically using epoxides. All right, so one synthetic target that we can use epoxides to make is called a glycol. That's a common name. A very common one is ethylene glycol with two carbons. Glycols are just molecules that have two OH groups right next to each other. Ethylene glycol is commonly used in antifreeze. A more descriptive name might be vicinal diol. Vicinal, remember, means on neighboring carbons. Di meaning two, all meaning alcohol. So two alcohols on neighboring carbons. This is a common synthetic target. One way to make them is from epoxides. So again, we could start with an alkene, react with MCPBA to make the epoxide, and in this case, react with H2O with an acid catalyst, so H3O plus. That's a mechanism that looks exactly like this one, just with a different nucleophile. We've seen this theme before. A lot of the reactions that we can do with water, we can do with an alcohol. We just get a slightly different result. So in this case, if we use water and an acid catalyst, we're going to protonate. Then we're going to attack sigma star CO, open up the epoxide, call sol to deprotonate, and I get my glycol as a product. I want to point out the stereochemistry of this. Because of the way the epoxide opens, the stereochemistry is going to give you the OH groups on opposite sides. Remember, we call that an anti-addition. So if you were to write this in a synthesis type problem, you could really just take your alkene and write two steps. First step, MCPBA. Second step, H2O with an acid catalyst. And that'll give you the anti-addition of your two OH groups. And I'm going to indicate that this is a racemic product. So if you need to synthesize a diol and you need your two OH groups across from each other, this is a great way to do it. In theory, we could do this under basic conditions as well. The problem with doing it under basic conditions is often reacting hydroxide with an epoxide. leads to rapid polymerization. So this reaction gets going, and it gets going quickly, um, where your OH minus attacks one epoxide, that opens it up, makes an intermediate like this, that can then attack another epoxide, open that up, and et cetera, et cetera, et cetera. You can end up with these long chains. So generally, this is done under acidic conditions, not basic. Um, it turns out, organic chemists like to try and find other reagents to do things. Um, and I throw this in partly because you don't get often to hear about the element osmium, but it has a really fun name. And so this compound, osmium tetroxide, can be used to form glycols as well. But in this case, it will give you a syn addition of the two OH groups. There are other reagents that can do this as well. So depending on what course you end up taking, they might offer different reagents. Um, but osmium tetroxide can be used to do a syn addition of the two OH groups. So if you're in a situation where you need to form a glycol, um, if it's an anti-addition, use this first route through the epoxide. If it's a syn addition, you're just going to use um, osmium tetroxide under aqueous conditions. I'm not going to show you the mechanism for that. You can look it up if you're interested. But these mechanisms involving metals tend to mm, look a little different than what we're used to. So that's it for Module 25. There are more reactions of epoxides that I'm going to show you in the next module, but um, in order to do it, we need to talk about a new category of compounds, organometallic compounds, that will allow us to form new carbon-carbon bonds with epoxides. So that's what's coming up.